Hello again. We should have what should be a short video this time. Today we're going to be talking about the definition of the derivative. This is sections 2.7 and 2.8 together. So the idea behind getting a derivative is we want an instantaneous rate of change. Now an average rate of change is fairly easy to find. If I have some time which has passed, for example, and I have traveled some amount of distance, then my average speed over that time would be the total distance divided by the total time. Or in other words, more mathematical terms, the change in y divided by the change in x. And this is my average rate of change. But that's not good enough for us. What we want is the instantaneous rate of change. I want to know how fast I'm moving right now, for example. So instead of having this secant line, but through 2 points, I want to have information about this tangent line through 1 point. My picture's not fantastic. I'll draw another one later. So the problem we are tasked with is finding the instantaneous rate of change of a function. Say here, I want to find the rate of change at exactly this one spot. Here I'll call this the tangent line because it is a line which is tangent to the curve at exactly one spot. And I achieve this tangent line through a bunch of secant lines in a nasty picture. But what happens is, as the endpoints of my secant line become closer together, I get a better approximation of what my tangent line is going to look like. But how do I calculate the slope of the tangent line? Because in order to calculate a slope, I typically need 2 points. I have a y2 minus a y1 divided by an x2 minus an x1. But with a tangent line, there's only 1 point. And it's not very helpful to say that the slope is equal to y minus y over x minus x, because that's just 0 divided by 0. We never know what that is. So what we do is we take a limit. So if I want the slope of the tangent line, so the instantaneous rate of change, or slope of the line tangent to the function, at x equals a is the limit of f of x minus f of a divided by x minus a. This has the effect of being similar to my slope between 2 points, y2 minus a y1 over x2 minus an x1, as x2 approaches x1, and I take a limit as they get very, very close together. This goes back to what I said about everything in calculus being the result of a limit. Now, similarly, since after I evaluate this limit, I'm going to have some kind of a function in terms of a, I can generalize this to just giving me a function. So I have a big OR here, and I have the limit as h approaches 0 of f of a plus h minus f of a divided by h. Now this is very similar to the other version I had written up above when I had a delta y divided by my delta x, because here my letter h represents my delta x. So the general form for the derivative of a function is denoted f prime of x, which is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. And this is what we need to use in order to determine all of our original derivatives. So for example, if I have my function equal to the square root of x minus 3, and I need a derivative of that function, I'm just going to pop it into this limit. I know that f prime of x will be equal to this limit, as h goes to 0, of f of x plus h minus f of x all over h. Or if I go ahead and plug in my function, I'll have the square root of x plus h minus 3 minus the square root of x minus 3 all over h. And I need to try to evaluate this limit. So, as you can recall, I don't like square roots, so I'll try to get rid of those, and I do that with a conjugate. So I'll have the limit as h goes to 0 of the square root of x plus h minus 3 minus the square root of x minus 3 all over h, and I'm going to multiply and divide by the conjugate. So that's going to be the square root of x plus h minus 3 plus the square root of x minus 3 all over, same thing, and I'll need to multiply this out. First up, I have x plus h minus 3, plus and minus, things that cancel, so I'll have parentheses x minus 3 in the second spot, all over h multiplied by my conjugate. Now if I distribute this negative up top, I believe I can cancel some stuff. I'll have an x minus an x, so those will cancel. I'll have a minus 3 minus a negative 3, which is minus 3 plus 3, so those will cancel. And I'm just left with an h on top. I have h over h. And this is kind of an amazing thing with derivatives. Every time you do the limit, generally all the stuff which does not contain an h is going to cancel away, leaving you with just an h on the top, which is perfect because this h is going to cancel with the h on the bottom, and that's going to let me evaluate my limit easily. So when I plug in h equals 0 here, I end up with 1 over h is 0, so I'll have the square root of x minus 3 plus the square root of x minus 3, so I'll have 2 times the square root of x minus 3. And that would be the derivative of my original function. These steps using the alternate definition of the derivative are more useful for finding the slope at a single point. Or give me the same, except I'm going to be factoring and canceling an x minus a instead of an h. So some properties that the derivative has is it's a linear operator, whatever that means. My favorite notation for derivatives is this, so d dx of a function f of x is going to be f prime of x. Now I have some properties here. If I have the derivative of a sum of functions, f of x plus g of x, this is the same thing as the sum of the derivatives. Similarly, whatever works for addition works for subtraction, so subtraction works as well. And if I have a constant multiple of a function, well, that's just going to be the constant multiple of the derivative, where c is a constant. And lastly, if I want the derivative of a constant, well, the constant function is just a horizontal line, y equals c. And the slope at all of those points is going to be equal to 0. So the derivative of a constant is always 0. And that's really all we can do with derivatives. For everything else, we have to try a little bit harder. However, we do have one extra true condition about derivatives, and that has to deal with continuity. So I'll say it like this. If a function f of x is differentiable, meaning I can take a derivative, meaning that the limit above exists, then f of x must be continuous. We only have a couple of different versions of discontinuities. There's the kind where we have a hole, and there's the kind where we have a jump. There's also the kind where you have crazy stuff happen with an asymptote, but that's really just another case of a jump. If I have the first type of discontinuity, then my limit fails because I need a function value to find my derivative at. And the second case would fail because the limit from the left and from the right for the derivative would be different, because they both center on the function value, and I end up with crazy vertical slopes over here versus horizontal slopes over here. So if it's differentiable, then it must be continuous, or equivalent words, if a function is not continuous, then it cannot be differentiable. So some basic derivatives we can immediately access are the power rule and the derivative of e to the x. Just so that we have some more interesting things we can talk about. It's the only reason that's included in this section. So the derivative of x to the power of n is going to be n times x to the n minus 1. We take our power, we put it down as a coefficient, and we reduce the power by 1. And the derivative of e to the x is everybody's favorite, because the derivative of e to the x is itself. It is its own derivative. So according to some of the properties we had in the previous section, if I'm looking for the derivative of 14x cubed minus 2e to the x, this is the same thing as the derivative separately of 14x cubed minus the derivative of 2e to the x, which is 14 times the derivative of x cubed minus 2 times the derivative of e to the x. And this first one, that should be 3 times x squared minus 2 times derivative of e to the x is e to the x. 42x squared minus 2e to the x. And if I wanted, I could take the derivative of that again. I can take derivatives as many times as I want. So that's denoted like this: d squared dx squared 14x cubed minus 2e to the x. Forgot to write the square. Which is equal to the derivative of the first derivative I found, which is 42x squared minus 2e to the x. And this follows the exact same process I did before. 42 is largely ignored. It's multiplied by 2x to the power of 1 minus 2 times e to the x, leaving you with 84x minus 2e to the x. You notice that the second term never really changed, because the derivative of e to the x is just simply itself. That's it for all of these sections. We're going to have a lot more to talk about next time when we cover all of the rules, and actually include the derivatives of sine and cosine, other trig functions, and deal with products and quotients of things. And not to mention the most important rule we're ever going to have, the ever important chain rule.